Welcome to an educational video series on inverted pendulum and controls. This is an optional video, and we will go over how to derive equations in Matlab from Part 1 and 2. We are going to use Matlab Symbolic Math Toolbox that will allow us to take derivatives and define equations in terms of variables. To define a variable, you need to specify next to SYMS. As you may have noticed, two of the variables, x and theta, have t in parentheses. This means that these two variables are time-dependent. Let's follow our notes side by side to understand how to achieve the same equations using Matlab. So first, we're going to define the ball coordinates in xm and ym and output it in command window. We format our output with fprintf and make our variable-dependent equations pretty by using a Matlab built-in function. Conveniently, it's called pretty. Now that we have ball positions, we can define its velocities by taking the first derivative with respect to time. As mentioned previously, x and theta are time-dependent. So when we write diff of x, Matlab knows that it needs to take a derivative with respect to time, since that's the only variable they depend on. And again, we display the equations into command window. Next, we need to specify energy states: kinetic energy, potential energy, dissipated energy. After we get our energies, we need to take derivatives with respect to the generalized coordinates for our Lagrange equations. Let's first tackle Lagrange with respect to x-coordinate. First term of Lagrange. Second term of Lagrange. Third. And fourth. Putting it all into one equation, we get our Lagrange equation with respect to x-coordinate. Please notice that Lagrange x is just a handle for this equation. We have energy derivatives on the left-hand side and force on the right-hand side. When displaying the equation, we utilize two more useful functions: simplify, which simplifies the equation, and isolate, that isolates a specified variable. In our case, we are isolating variable force. And then we need to isolate x acceleration on one side. It will later be substituted into theta double dot because we do not want to have x double dot and theta double dot together in equations. We repeat the same steps to get theta double dot, our first term of Lagrange, second term, third, and fourth. Now we put them all on one side and force or torque on the pendulum arm on the other side. Please notice, torque applied is 0 since we are not inputting force directly onto the pendulum arm. Now that we have accelerations, we need to substitute theta double dot in x acceleration and x double dot in angular acceleration to get our final equations for accelerations. This was the last step of Part 1 of the educational series. Now that we have our nonlinear equations, we can linearize them. First, we put them into a vector called Cauchy equations. Then we define all states for Jacobian matrices. Then we define the Jacobian matrices themselves with all the derivatives with respect to each state. With the substitute function, we substitute our states to our points of linearization. Please notice that third state, which is our theta, is pi for pendulum pointing down and 0 for pendulum pointing up. We do the same thing for the input Jacobian and get our linearized state space that we used in Part 2 of this educational series. And this is everything we have done so far in the educational series. Symbolic Math Toolbox is a powerful tool, but please do not get too dependent on it. Not only that, you might get scolded by your older professors saying that we got too lazy. But it also needs to be double-checked. Personally, I derive everything by hand and then with Matlab to make sure that my results are identical. I hope this tool will be of great benefit. Now, let's go to our final part to see how to derive full model for the inverted pendulum.